Hey guys, so this will be 23.4 through 23.6 for physics. We're going to talk about refraction and Snell's Law, and also talk about total internal reflection. So the first thing you need to understand is that light, it has a speed that we consider the speed of light, and we call that the speed of light in a vacuum. So what that means is that when we're talking about traveling through space or through a vacuum where there's no air, there's no matter to get in the way, that light will travel at the speed of 3 times 10 to the 8th meters per second. And that's the same for all electromagnetic waves. We're going to specifically be talking about light, but it's true for all EM waves. But once that electromagnetic wave enters into another medium, another material to travel through, the atoms slow the speed of light down. It gives it a different velocity. The speed of light is always going to be 3 times 10 to the 8th. However, the velocity of light might be slower, and so we're going to see how that's affected. So we have what's called an index of refraction. It's a property, it's a characteristic of different materials or properties, and it has to do with how much light will slow down through that material. And so over here, this is on page, you're going to want the page number here, 642. On page 642 we have a table that we're going to reference in homework questions and possibly on test questions, where we talk about different materials and their indices of refraction. And the definition for an index of refraction can be found right here. N, the index of refraction, is the speed of light divided by the velocity of light in that material. And for this table, we're using what we're going to call yellow light. It has a wavelength of 589. It is more complicated than that in that different wavelengths of light will change their speed more or less depending on the material. So this is the index of refraction for a wavelength of 589 nanometers. If I did a different color of light or a different EM wave, it'll change how much it speeds up and slows down, and therefore how much it bends. When we talk about refraction here in just a second, we'll talk about the bending of light. This is why rainbows occur, why we have why we get the full spectrum to spread out through a prism, because depending on the wavelength of light, it will speed up or slow down more inside of a different material. So what we want to start with is just that the index of refraction is the speed of light divided by the velocity of light in that material. So we can calculate the index of refraction of lots of different materials. You notice on this table that diamonds have the biggest index of refraction on the table listed. That's part of why they tend to have what we call the brilliance or the brightness that they do. The light gets in there, and depending on how we create those surfaces, we can get light to spread out in lots of different colors and be very shiny and pretty. Second thing we're going to talk about is Snell's Law and refraction. So in Snell's Law, we learned that depending on the material we're going from and going to, we have our incident ray. Now some of that light will reflect. It will reflect, bounce back off, but some of it is going to enter that second material, and as it does, it is going to bend either towards the normal or away from the normal. It depends on whether the light is speeding up or if the light is slowing down. If the light is going from a fast-moving material, right, so through the air it's going to move fairly quickly, but when it hits water it's going to slow down, it will bend towards the normal. But if I'm going to a material where the light can speed up, it will bend away from the normal. You'll see that theta 2 in this second case is bigger. Keep in mind we always measure against the normal, so that's really important. This has to do with why things are distorted in water. When we look at something in water, things don't look quite right. If you think about it this way, we'll look at this picture here. The light from the girl's feet is down here. It's heading up, it hits the surface, and it bends. And because it speeds up, it bends downward away from the normal. Well, he doesn't know that. His brain doesn't process that. And so he thinks that it's a straight line shot to her feet. So if you look at this girl, she looks like she has very, very short legs relative to the rest of her body. So it's very distorted when we look at it from that perspective and that angle. And so it's important that we understand how to correct for that in the way that we look at things when we look through different materials. When we look through, when we look at a star, for instance, we have to recognize that it's coming from a vacuum into our atmosphere. And that means there's going to be distortion in what we're seeing. And so it's important that we understand how to correct for that distortion. Well, Snell's law boils down to a very simple formula that says the index of refraction of your first material times the sine of theta 1. Now remember, theta has to be measured against the normal. This will equal the second index of refraction times the sine of theta 2. This actually has a lot to do with the law of sines. If you understand the law of sines, you'll understand a little bit about why we end up with this formula. It's very, very similar. This is called Snell's Law, sometimes referred to as law of refraction. It tells us how much light bends. And so we can go through lots of different materials, and as we go through the material, we can see how much bending of light there is. The last thing that we need to talk about in this section is called total internal reflection. We use this in fiber optic cables, but it's essentially that if we come in at the right angle, the right initial angle, there's a point at which we can make it so that the light doesn't actually leave the initial material. Now, a couple characteristics have to be true. Now, here's our formula. It says that the sine of what's called the critical angle, so this angle where it starts to happen, okay, is equal to N2 over N1. Essentially what we're saying is we don't want the light to exit. We want theta 2, okay? We want theta 2 to be 90 degrees. Because if it's 90 degrees, it's going to fall right on the edge. It'll just follow the surface. If we let theta 2 be 90 degrees, well, the sine of 90 is 1, and so we end up with this formula. What's cool about it is once we let theta c get bigger, once we get bigger than theta c, right? So this is my theta 1. If theta 1 is greater than our critical angle, then all of the light is going to bounce back inside the water or material that we're in, and it won't exit. What that means is that we no longer lose any of our light or our intensity out into the second object or second material. Well, this is really cool because then we can do some things with fiber optics. And we can take light and use it, which travels extremely fast, very well. We can travel it through a wire that's right next to another wire. And we can send, normally if you think about, well, not wires, but a fiber optic cable, so it's going to be a glass wire, if you will. We can shine a light through it, and if we have the right initial conditions, we can prevent the light from spreading into another line, another fiber optic cable that's next to it. And so we can send a signal like this. We can have the light from this A come all the way through, and it will stay in each of the cables it belongs in. This allows us to make some very, very flexible ways of shining light in any direction that we want. Think about a flashlight, a traditional flashlight. You shine light, it's a rigid, a hard object, and you can't really move it around. But if we could connect to the end of that flashlight fiber optic cable that we can bend and twist and do loop-de-loops, whatever we want, and we still get the signal through the end clear as it was when it came in, that's a really big deal. And so we can use fiber optic cables to send information, more than just sending light. Actually, using the wavelengths and pulses, we can send information through the fiber optic cables faster than we can send it if we have to send up to space to a satellite and then that satellite send it back. That travel time can be cut down significantly if we're able to send it in a direct line across the ground or on a power line. And so total internal reflection is really, really useful and important. And hopefully that helps you understand everything that you need to be able to get through the homework today. Good luck, and we'll see you in class.